Lithium-ion batteries have become the most important lithium application and storage technology in mobile and mobile applications, such as laptop, cell phone, smartphone, and electric vehicle medical device. Lithium-ion batteries are rechargeable batteries with high energy density, mainly used in mobile devices. These batteries are popular with automakers because of their small size and lightweight, as an alternative to the nickel metal batteries used in electric vehicles. Therefore, in order to make the battery power system available to play a better performance while ensuring security, it is necessary to optimize the design of the battery cooling solution.
So the methodology was started by sketching the base geometry of the lithium-ion battery packs, which containing 32 cells of batteries. The locations of inlets were located at the upper part of the front wall, while the outlet was located at the lower part of the battery. So the force field inside the lithium-ion battery pack is set as air, while the material property for the batteries is set as aluminium. The tetrahedral mesh is used in the elements type. So here is the boundary condition for our project. Our free stream velocity is set as 2.8 meters per second, while the battery box was set as non-slip wall, while the heat conversion will happen on the wall also. On the next slide, the boundary needle selections in ideal geometry is shows. So in the solver settings, the K epsilon is chosen for the vicious model because it is the most common to simulate the mean flow characteristic of the turbulence flow. So next, the solutions of discretization component is shown at the table below. So lastly, in residual settings, the convergence criterion were set in 0.001.
For the mesh sensitivity analysis, three different methods with various grades are applied to investigate the accuracy of the result. As a conclusion, the mesh 2 was chosen because when further increase the mesh quality to mesh 3, it only yields a minor changes and hence mesh 2 with lower number of elements is selected. For the result and discussion part, we will discuss about the title stated below. First is the velocity streamline. The velocity streamline is concentrated at the top of the battery pack domain as we set the inlet at the upper part, and the velocity streamline does not enclose the battery pack evenly. Next is the temperature distribution contour. The temperature of the cells increase along the length of the battery pack when the cool air is flowed in from the inlet. The lowest temperature is indicated at the part close to the inlet, and the cells maintain at a higher temperature, especially at the bottom part near the inlet.
The figure above shows that the pressure of the frontal part of the battery is lower than the rear part. This is because the cooling is not occur at the frontal part and the airflow rate is lower. However, for the figure below, the outlet shows that the pressure is lower. This is affected by the ambient pressure and the airflow rate at the outlet is higher.
Based on the velocity contour as shown, we can observe that there is a higher velocity of airflow heat straight to the batteries near the inlet position. So as a conclusion, the temperature is lower where there is a higher airflow velocities and higher mixing of flow at the front row of the batteries. Whereas, once the flow starts to flow in between the row, there is a less airflow or air between the adjacent cells along the length of the battery pack.
Next is the graph of temperature against length of housing. There are three lines plotted at the center of the domain, and the graph showing that the temperature is fluctuated and inconstant. But at the end, the temperatures is all higher than the initial temperatures for all three cases. Next is the average temperature at different velocity inlet. From the graph, we can observe that the average temperature is decreasing as the velocity inlet is increasing. This is because as the velocity inlet is increasing, the heat release rate also increasing. Next is the uniformity temperature at different velocity inlet. From the graph, we can observe that the uniformity temperature is gradually decreasing as the velocity inlet is increasing. This is because the temperature difference between the maximum temperature and minimum temperature is reducing as the velocity inlet is increasing. In conclusion, with the increase of inlet velocity, the cooling performance improves gradually. Under the same number of battery, increasing the velocity of inlet can improve the cooling ability of battery pack, and our design for inlet can improve the consistency of battery temperature.